Yes, thank you for introduction. So I'm Yuji Matsumoto, a postdoc from CFC Naoje. So today, I will provide one more ejection talk, ejection dynamics talk. But in this talk, I focus on the super Earth and super Earth and Roma stars. Okay, so so this is population of the observed exoplanet. So, but so I only picked up transiting planet and RP planet. So there are actually no microlensing planets. And so these planets are located at the inner orbit. So inner than most are inner than 1 AU. And I plotted these planets on the diagram stellar mass. This is vertical axis is stellar, horizontal axis is stellar mass, and vertical axis is planetary mass. So thanks to the recent instrument like IRD observation, several IRD or TRAPPIST observation, so we come to know the population of the planets around very low mass stars, so like a 0.1 solar mass stars. So, as you know, so there are many gas giants and super Earths. So here gas giants and super Earths. So here I call super Earths, so which have a mass around 10 Earth mass. So these populations are super Earths. So these are so many around one solar mass stars. So if you look at these groups, so like 0.1 solar mass stars, so these populations are very sparse. So also we already detect one Earth mass planets around the 0.1 solar mass stars, but these populations are relatively sparse. So it's kind of strange thing. So since these massive planets are more easily detected, so more easier than these populations. So at first we expect there are many planets, but actually there are not so many. So we can interpret this by two scenarios. So one is how to form these planets. So 10 Earth mass planet around 0.1 solar mass stars. So like so if there are no less materials, it's very hard to form. But in this talk, I focus on the ejection scenario. Uh, so these are not brought to such super Earths by ejection. So okay, so I can almost skip this. So as you yeah yeah, so many previous already introduced this kind of scattering. So in a single scattering event, so planets get escape velocity, and it's corresponding to the so escape eccentricity is like this. So some introduced similar values as a Sakharov number. So it's corresponding to this equation. Uh, mm. And so, as you can see, so there are dependence on planetary mass and stellar mass. So if we consider this escape eccentricity equal to unity, we can draw a line like this. So if the planets over this line cause ejection, so easily cause ejection. So we can explain the absence of planets like here, so from the ejection, but here, so also sparse region. So I try to explain this absence by ejection. So this is our motivation. So the ejection cause 10 Earth mass planets around low mass star world. So this is our motivation. Then we set up this kind of stars and planets, and in our simulations, we performed many body simulations, and in our body simulations, stellar mass is a parameter, so we equals the mass of mass stars to this very low mass stars, 0.056, so this is about this value. We put plot planet as isolation mass, so this according to this profile, so like MMS, so minimum mass solar media profile, and we can derive this, so there's dependence on the stellar mass. So when we plot the initial plot planet on the this planetary mass and stellar mass diagram, this is our initial plot planet. So innermost planet has a smallest and outermost has a massive, the most massive one. And we consider three cases. So this is the MMSN value, and 3 times and 10 times. So we consider these and perform simulations. So this is the one result of the typical evaluation. So this is a case for the one solar mass case, and this is a case for the 0.056 or lowest stellar mass case. So surface density is this value, so the initial total mass of plot planets are the same. And so at first, so I explained this case, one solar mass case. There are usually many plot planets and planets cause also, so this is center axis and center and time evolution is a center axis. So initially plot planet cause water instability and collide with neighborhoods and grows up, and eccentricity is gradually pumped up, and finally 4 planets are formed. So these must so like around 10 Earth mass, it's super Earth mass. And this kind of so similar mass systems are common. Also, detected in the by the observations. So this is kind of one good scenario to explain the observed exoplanets around one solar mass stars. And this is a case for the lower mass stars, as you can easily see. So there are two ejections. So the planets are ejected, and finally, so only 2 planets are formed. So their experience very drastic dynamical evolution. So as you can see, so this ejection is caused by the multiple scattering event. So if you look at this red planet evolution, so it's scattered here and for ejection. So blues also experience multiple ejection. So actually, so this kind of evolution can be seen in the slide in previous speakers, and so multiple scattering event is important for ejection. So since I plotted the result of my parameter study, so this is stellar mass, and most massive planetary mass is plotted. So in the solar mass case, the planets are accreted. As you see in the previous slides, the planets cause collisions and accretion, and the most massive planetary mass increases as stellar mass decreases. So this can be interpreted as by the Hilarious. So initially I put plot planet in this range, and as stellar mass decreases, the radius becomes larger, then so a protoplanet can interact with more the distant one, and it makes this increasing line. But this trend stops at uh, some value, so some stellar mass. So this is because ejection limits so this position growth. So because of this ejection regime and this is collision regime. In collision regime, so protoplanet can collide with Atlantic and grow up. But if the stellar mass becomes smaller, escape eccentricity becomes larger, then so ejection regime occurs, so growth are limited by ejections. So as you can see in the previous slide. So this kind of ejection limits the growth. So the boundary of the ejection regime and collision regime is this value is escape eccentricity is equal to the 0.4. And this is so result from evaluation. So the I brought its ejected planet mass and ejection rate, ejection mass rate. So ejection occurs so this line is ejection regime boundary, and so these are the same stellar mass. Ejection regime, so the ejection occurs before the ejection regime, but after ejection regime, so the ejection rate becomes larger and growth limited. So only lucky collision makes the accretion, and most as stellar mass becomes lower, most goes to the scattering and ejections. So in the so these extreme case, so very low mass cases, so more than 10 or 20% of the total mass are ejected. So this corresponding to in our simulation, this corresponding to so like 1, 2, or 2, 3 planets are ejected from these low mass stars. So then so we can now plot so these new boundaries of escape eccentricity go to 0.4. So this can will reproduce this sparse region. So ejection limit would would occur in this region by the multiple scattering event, and this can reproduce this sparse region well. So if the scattering around this region occurs, so the planet scatters, so these mass planets or lower mass planets, then so I think it will contribute to these masses. So this figure is taken from Simpson's paper. So these small planets can be ejected from these low mass stars. So this is my total. This is summary slide. So we perform so observation is 0.1 solar mass stars do not tend to host many superstars, but it's commonly detected around 1 solar mass stars. We perform embodied simulation, systematically surveying the parameter of stellar mass and found the multiple scattering event is important post ejection, which causes limitation of the growth, and ejection reproduce observational trend well. And what is interesting of this point is these sub-2 super-Earths are ejected from these low mass stars, even from the inner region, very inner region, so inner than 1 AU and without gas giants. So I think this is the interesting point for the population for free floating planet. Yeah, it's almost time. Thank you.
Any questions? Yes, you.
Sir, Mark, I want to take short classes around most of my astrological do you know how much of that is just observational bias and if anyone is corrected for it?
Actually, I don't know the paper discuss about this occurrence rate. So I think these are more easily detected, but there are no occurrence rate discussion.
Any questions? I think in the previous talk, the sound says it's taken so long time to eject the planets from the normal star, and that seems different from your result. So what's the main difference? Is it only the you are counting the double scattering and the previous talks are not?
Actually, I don't think it's so different. So this is because I brought this unit of year, and if we consider the unit of total period, so it's like 10 to like 6 or 7. So it take the 6, 7 orbits. It's maybe not so different from the systems.
Any questions? Yeah.
So I have a comment on even the questions, the occurrence rate and the planets in the sparse regions. So, with the cameras and the speed and solar radially try to find planets larger than 2 or 3 times Earth's using the near infrared Doppler. So I think the detection limit should be larger than 2 to 3 times Earth's for the other measurement, especially for the 0.2 and 0.5 times solar. So that unfortunately is 0.1 for the smaller stars. It's quite difficult to monitor the different surveys using like infrared measurements. But traffic survey suggested. So I think that we cannot find the bunch of the planets around such kind of cool stuff. I mean, so it's 0.1 times solar mass and the smaller ones. So that's why I think the sparse regions can be seen in the diagram shown by Yuji. It's kind of the real. It's kind of real, especially for the about the 2 or 3 times the essence. But the normal, we don't know that.
Any final questions? No? If not, let's thank Yuji again.
Thank you.